Hi, I'm Karen Jex, Senior Solutions Architect at Crunchy Data, and today I'm presenting Managing Postgres at Scale, Challenges, Tools and Techniques. So I'm going to be talking to you about some of the things that you might encounter as you work with Postgres at scale, whether that's managing huge databases, whether it's managing many databases, databases with large numbers of users or high transaction throughput. And we'll look at some of the things that you can do, some of the tools that you can employ to make that easier. So please stay tuned. Okay, so let's get started. Who am I? I'm Karen Jex, so Senior Solutions Architect at Crunchy Data, but also a PostgreSQL Europe board member and chair of the recently formed Postgres Europe Diversity Committee. And here you can see that I come to my current position with a database background, so 20 years as a database administrator. And the talk today is based on experience, past and present, from customers who are actually working with Postgres at scale. So, what do we actually mean by at scale in this context? Well, it could be massive databases, and the size of a massive database varies, evolves over time. So, at the moment, that might be something over tens of terabytes in size. It could be a park of hundreds or thousands of databases. It could be particularly busy databases with a lot of concurrent users or very high transaction throughput. It could be databases where you've got a mixture of your day-to-day transaction processing, your OLTP activity, and complex queries for analytics. Or, as is usually the case, it could be one or more of those things. So this is what we're going to have a look at today. We will look at what some of the challenges are of managing databases at scale, and then some of the things that you can do, some of the tools and techniques that you can put in place to make that easier. So some database design and architecture aspects, monitoring and alerting, things that you need to do for high availability and disaster recovery, how you can optimize your database for a hybrid workload, and then some maintenance tasks, in particular, auto vacuum. So each of the aspects that I already managed of databases at scale comes with their own set of challenges. If you're working with huge databases, then you've got to store large data volumes. You've got to deal with tables that have got millions or more rows. That might mean you've got bulk loads to do. You've got to think about data archival. You might have slow queries that are running over huge volumes of data. Maintenance operations can take a long time, things like re-indexing, vacuum, etc. And you might even run up against hardware limits if you're using all of the resources available to you. If you're managing hundreds or thousands of databases, you're likely to encounter scaling issues. So you either might need to keep increasing the number of people that you have in the team managing the databases, or the people in the team are going to only be able to do firefighting because they won't be able to keep up with all the necessary tasks. Or better still, you would put some automation in place so that you can handle more databases with a small team of people. It's difficult to keep things consistent across a lot of databases, so you'll get things like configuration drift. Maintenance tasks can be very time consuming, so just as with huge databases, but this time because you've got to perform the tasks across all databases. You've got things like security that needs to be implemented across all the databases and monitoring that needs to be in place for all of the databases. If you've got very busy databases, you can encounter things like lock contention, potentially deadlocks. You could have too many concurrent database connections. You could have slow queries. You could have write bottlenecks. You could have I/O saturation. And you could potentially have issues with checkpoints and replication lag that you need to monitor and manage. If you've got hybrid workloads, then you can have other issues that come along with those. You've got workloads with competing needs. So you can have contention for resources. You could have conflicts with indexes. You could have to make sure that you carefully configure your database to be able to manage those complex, long running analytics queries and make sure that doesn't impact too much your day to day activity. So we'll have a look at some of the tools and techniques that we can put in place to help with some of those things. First of all, some database design and architecture considerations. So you might have to think about things like multi-tenancy. You might have many different users using your databases. You'll have to think about what kind of infrastructure platform you want to use, what operating system, what type of storage. You might want to look into partitioning, and you'll probably need to look at indexing. So multi-tenancy, as I mentioned briefly, that is where you've got multiple applications, customers or users, whether that's internal or external, all using your databases. Um, and if you've particularly got a situation where each of your environments or each of your database clusters has multiple um, users or applications, then you've got multi-tenancy considerations. So I've talked about this in detail in a previous talk on multi-tenancy, so I won't go into it in too much detail, but there are many different ways that you can implement a multi-tenant architecture in Postgres. Um, and to decide which is the right one, you need to make sure you balance the requirements of your different tenants. So you need to figure out how to co-host them and make sure that they have the isolation that they need, that they're going to get the performance that they need, that either you've got them all in one place so that you can manage them together, or that you've got them separate so that each tenant manages their own environment. When it comes to platform choices, you might think either of running your environment in bare metal, on VMs, or in Kubernetes. If you have a small number of huge databases to manage, then you might need predictable high performance for high numbers of transactions. You might need isolation from other workloads. You might need isolation in terms of security and that kind of thing. So, in that case, you may well be choosing a bare metal architecture. VMs, on the other hand, let you manage more databases on fewer physical servers, but you still get that isolation for your database environments. It's much easier to provision a new VM than it is a bare metal server, and you can scale resources more easily. You've got a choice of cloud providers as well that will make VMs available at the press of a button or via an API. So that can obviously be a really convenient choice if you've got a larger number of databases to manage. Running databases on Kubernetes is extremely useful if you've got large numbers of databases to manage and you want as much self healing, scaling, and automation as possible. Partly because Kubernetes automates a lot of the things that otherwise make managing large number of databases such a headache, including things like provisioning, um, scheduling, the self healing, creating services and networking for you. Um, Providing persistent storage via persistent volumes, um, and partly because you've got Postgres operators for Kubernetes available for you, so such as the Crunchy Data Postgres operator, which CPK uses, Crunchy Postgres for Kubernetes. Um, a Postgres operator takes care of a lot of the day-to-day tasks that a database administrator would otherwise have to perform. So your high availability, backup and recovery, security, monitoring and alerting, creating databases, database maintenance tasks, and even performing minor and major Postgres upgrades for you. You just declare what you want your Postgres cluster to look like, and the operator, Kubernetes, and the tools that are integrated will take care of the rest, keeping your cluster in that state that you defined. Even if you're not working in a Kubernetes environment, then automation is hugely important, and it's critical if you're managing a lot of databases so that you can have things repeatable, um, predictable, and you know what's happening and how things are working. If you're working with huge tables that can become difficult to manage, so for example, maintenance operations could start to take too long, um, perhaps you want to be able to create table spaces so that you've got separate storage volumes for some of your data, then partitioning is a really useful way to split a single large table into multiple smaller, more manageable tables. So imagine that this table, for example, contains millions of rows rather than just the 9 that we can see here. With partitioning, you conceptually still have one single large table, but it's physically split on the partition key into smaller, more manageable tables. Those are the partitions. So the partition key that you choose will depend very much on your use case. It depends on the way that your data is accessed and managed. So here, for example, I've used the ID as the partition key, and I've created partitions based on a range of IDs. So we've got IDs 1 to 3, 4 to 6, and 7 to 9 in those partitions. So as I said, it is important to choose the partition key carefully depending on how your data is used. If your queries mainly access data based on year, for example, then it would probably be much more sensible to partition based on year. That way, a query for 2022 could go directly to the 2022 partition to get the rows it needs and ignore the rest of the table. If your data was mainly accessed by region or some other field, then that might be the partition key that you choose. Partitioning is also really useful for things like removing large quantities of data. You might have data in your database that you're not allowed to keep for longer than a certain amount of time, or that's taking up space that you don't want to use. So you'd ask yourself the questions about how long you're allowed to keep data, how long you want to keep data. Do you want to delete the data, or do you just want to archive it to somewhere else where it's still available, but perhaps not as immediately? Do you want to do what we call a soft delete, so just mark the data as deleted, or do you actually physically want to delete the data? And partitioning can help speed up and make very easy that kind of deleting of old data. So here, for example, if you needed to delete all of the rows from 2022, if you did that as a delete operation, it could be a very costly, time-consuming operation. You'd probably also then need to regenerate statistics. You'd need to maybe recreate your indexes, form vacuum, etc. On the other hand, if you partition your table by year, then you've got a few simpler options open to you. You could, if you wanted to, just drop the entire partition for 2022. If you want to, before dropping it, you can detach it. You can turn it into a standalone table. So that could be useful if you wanted to use that to aggregate some data, or if you wanted to perform a final export or something like that. Indexing is very useful and necessary in a lot of the situations that we discussed. You can create indexes on multiple columns. You can create indexes on column expressions. You can create indexes that are just partial indexes so that you're only actually indexing the data that you're going to filter on. So that can help make your indexes smaller and more efficient. So indexes will help speed up searches that are based on values of columns in the index. So things that filter, and they can also be helpful for other things. They will enforce things like primary and unique keys, but at the moment we're looking at ones that are, useful for performance purposes. So you've got various different index types available to you in Postgres. They're useful in different situations, and I've linked to the documentation so you can look up more about those. But the default type and the one that's used in most situations is the B tree, balanced tree. The main thing to be aware of really with indexes is that you don't want too many. You want to create the indexes you need, but they take up space and they need to be maintained. So they can actually slow down operations that modify data. So you just want to be careful not to create more than you need. So here I've just given an example of what a B tree index looks like. So it's a multi-level tree structure. It's got a single root or meta page. It's got multiple or one or more levels of internal pages, and each of those points down to the next level. And then there's a single level of leaf pages, and each of those contains tuples that points to the actual tables in the row. So this index represents an index on a beer table, on the beer type. And I've just shown the example for how the leaf page there would contain the pointers to all the rows that contain the beer type red ale. Monitoring and alerting. So you need to make sure that you've got the monitoring, logging, and alerting in place that will make sure you know what's going on in your database. So if something's going wrong, or if you think something might possibly go wrong at some time soon, you can react quickly and make sure that doesn't happen. The ideal, if you can, would be to have some kind of integrated logging stack that will export database statistics for you, that will then send those statistics to something like Prometheus, where you'll um, define metrics and alerts, alert manager that will send off alerts to whatever system you want to use to be told of any issues, and something like Grafana where you can define dashboards so that you can keep an eye on what's going on in your databases. You preferably want all of that to be automated for you, and you want to be able to turn it off for particular databases, because if you're performing a planned maintenance operation, for example, you don't want lots of noise going to the people that are having to manage and react to those alerts. Even if you don't have that kind of setup, then you can get a lot of useful information just from your Postgres logs. It's important to make sure that you've got some parameters set to make sure that you get the information in there that you need. So I've just given a couple of examples here. So for example, log min duration statement will write to the logs any statement that any completed statement that ran for longer than that given time. So here I've given an example of 1 second, but you'd set that for whatever counts as too long in your system, and is very useful for debugging purposes or in development, but just be very careful in production because you could end up generating a lot of noise in your logs. And the other one that I've shown is the logline prefix, because by default, you don't get much information in logline prefix. You just get the um, timestamp and process ID. So you can set that to include a lot of different parameters and whatever text you want so that it gives you useful information about who's doing what, where, when in your database. Another useful tool that many people use with Postgres is pgstat statement. So it's an extension that you need to add to your shared preload libraries. Then you can create the extension pgstat statements in the database that you want to use it in. And once you've done that, you can query pgstat statements to get information about long running or frequently executed queries. A little word on high availability and disaster recovery. So even if you're not managing lots of databases, you're likely to need some kind of high availability in place. Certainly, once you've got hundreds or thousands of databases to look after, you want as much of this to be automated as possible. You want to know that even if you're busy doing something else, if something happens to your primary database, one of the standbys is going to take over. Everything's going to be put back in place and be back up and running, so you won't lose time and you won't lose data. So this is just a diagram showing one example of how that kind of high availability architecture might be put in place. And I've given the links here. I'll share the slides so that people have got access to all of the links that I share in them. If it's not properly configured and monitored, then wall archiving is something that does tend to trip people up sometimes, and it's something that can cause issues in a busy database. So it's very important to make sure that you monitor, check that your walls are being archived to your backup repository as expected, check that your online wall directory is being cleared down as expected. Um, Make sure you're alerted if there are any issues with wall archiving. Make sure there's nothing preventing this from happening. Otherwise, you could end up finding your entire system grinding to a halt, and then there'll be some kind of emergency as you try to fix it. Um, I assume that you're using a tool such as PG Backrest to take regular database backups. As mentioned at the beginning, if you've got huge databases, then full database backups can start to take a long time, and they're obviously going to take a lot of space. So you could consider the frequency of your backups. Um, Perhaps you can take less frequent full backups and replace some of those by incremental or differential backups. So an incremental backup will only back up the changes since the last backup of any type, and a differential backup will back up the changes since the last full backup. So those will usually be faster and take less space than a full backup, but you just need to be aware and test your recovery to make sure that that still fits your requirements, because Postgres or PG Backrest, the tool that you're using, will need to combine those backups to get you restored, recovered, and back up and running if you need to restore. Okay, and then some words about optimizing for a hybrid workload, because a lot of people seem to be in this type of situation at the moment where they have both transactional and analytic activity going on, either within the same database or within a related environment. Configuration parameters are important for any type of workload, but particularly important in this case where you've got potentially competing workloads that don't necessarily have the same needs. So some parameters have to be set for the entire Postgres instance, and for those you need to carefully work to find a compromise that will work well for both types of workload. For the ones that you can set just for specific users or individual sessions or transactions, you can create, for example, an analytics user, and you can set the appropriate configuration parameters just for those users. So we'll just look at a few parameters for now. So database connections, max connections, you want to make sure isn't too high in general. So default's 100. We usually say maximum of a few hundred concurrent connections. If it looks as though you're going to end up with a lot more than that, for example, if you've got a lot of users or a lot of applications sharing a Postgres instance, then you'll probably look at something like connection pooling with a tool such as PG Bouncer. And you could look at creating a separate pool for your analytics connections, making sure that there aren't too many of those because they will be resource heavy. And then I'll just go very briefly through these. I will leave the links so that you can look at more information. WorkMem, you might need to increase for sessions that are performing large sort and hash operations. So that would include some of your analytics queries. You can make sure that it's set correctly by checking for temp files. So if temp files are being created, it implies you might need to increase that. You probably don't want to set it a high value for your entire instance, because you'll end up using a very large amount of memory. So you probably just want to set that for specific sessions that need it. Statement timeout: if you think you're going to have long running analytics queries that could cause a problem for your other workloads, then you could set a value for statement timeout. That means they are cancelled if they run for too long. We spoke briefly about indexes in general, but for a hybrid workload, you will specifically need to look at that, because analytics queries will probably need very specific indexes, particularly indexes on expressions. But again, it's very important not to create too many indexes, because you don't want that to have too much of an impact on your day-to-day transactional activity. For analytics, it's very useful to pre-calculate data, so you can create things like stored generated columns and materialized views. So a materialized view is a physical copy of your query results. So you've got that pre-aggregation. You refresh them as needed. So you would need to set up some kind of cron job, for example, to refresh the data as needed. And you can index materialized views. Best way of optimizing something is generally not to do it. So if you can avoid performing analytics activity on your application database, that's great. If you can have a separate analytics database. If you don't have a completely separate analytics system, then you can offload the activity to one of the standbys. And this works not just for where you've got a hybrid workload with analytics, but also for any type of read-only activity. If you've got heavy read-only activity, then you can offload some of that to a standby database to take some of the load off the primary read-write database. And you can also use a logical replica to do that kind of thing. Logical replication is more complicated than physical replication, and it has caveats, but you can replicate just certain objects. You can replicate to and from multiple targets. So you've got a lot more flexibility there. And then finally, in the maintenance tasks section, the thing that comes up the most often here is auto vacuum, which is described in the docs as optional but highly recommended. I prefer to be a bit more firm than that and say, please leave it switched on. But if you've got very heavy workload, very large tables, etc., then the default settings might not be enough to keep auto vacuum running as you need it to prevent table bloat, etc. So there are some parameters that you can set to make it work more efficiently. I won't go into these in detail. I will leave them here. I will just mention them. So you've got the max workers, the number of processes that can run at any one time. You've got how long it will delay between auto vacuum runs. And then you've got various thresholds that you can change. So if you don't think that auto vacuum is being triggered enough on a particular table, you can change some of these threshold values and scale factors, which will allow for the table sizes. You can change some of those so that the vacuum will be executed when you need it to be. So, just as a summary, we had a look at what we actually mean by Postgres at scale, talked about some of the different challenges that come with managing databases at scale, and then looked at some of the things that you can think about, some of the things that you can do to actually mitigate some of the risks and work around some of those challenges. So, making sure that your database design and your architecture choices reflect the needs of your environments, make sure that you've got monitoring and alerting, automate as much as possible, especially things like your high availability and disaster recovery. Looked at specific optimizations for hybrid workloads, which is quite a special use case. And then a brief look at maintenance tasks, in particular auto vacuum. So Obviously, a short talk isn't enough time to go into all the details of all the things that you might encounter when you work with Postgres at scale, but hopefully this has given you enough of an overview and some of the most important things to look at so that you've got a good idea of where to start. And I would love to hear more. I'd love to answer your questions. So please do get in touch. Thank you.